Okay. Um, Unfortunately, this is going to be our last class meeting of the semester because I have a graduate council meeting that I have to attend virtually on Friday. And so our hydraulic engineering class on Friday will be a recorded lecture video from a previous semester. So I'll email you the link for that. It's going to include an additional practice related to today's material. So you'll get that. Um, Remember that homework 11, you can submit that as late as 11:59 p.m. on Friday. And the reason for the extended deadline is just because you may need some extra time to work on the standard step problem that's in that assignment. We're going to cover one example today on the standard step method, but you'll see another with Friday's class. So that gives you some extra time to submit the homework assignment. On the subject of the final exam, remember that our test is on the afternoon of Friday the 1st. So that will be from 12:45 p.m. till 2:45 p.m. and in our class meeting on Monday I went over some of the particulars for that test. I mentioned that, for example, you should work alone without any collaboration with another person. You can use your homework assignments, you can use your textbook, you can use the computer. So if you have any questions about these announcements, I could answer them now, or if anything pops up in your mind as you're working, you can send me an email. Of course, I will provide instructions with the exam, so you don't have to remember exactly all the details because that'll be included with the test itself. Any questions? All right. Well, today we're going to work on another approach to predicting gradually varying flow. Remember that gradually varying flow are those long water surface profiles where we have some sort of an obstacle or something that's causing non-uniform flow, and we want to predict how the depth is changing in the direction of flow. And the method that we did in Monday's class, the direct step method, is one approach. And what we were looking at when we went through that example as an illustration was trying to predict how long the backwater curve is. So you can see in this diagram down at the bottom of the screen, our approach, what we did was we divided that curve up into segments and we linearized within each segment. And so what we did was we found, for example, the depth of water that was just upstream of the broad-crested weir, and at this location we knew the depth, and what we tried to calculate is what was the segment length to go upstream some distance to another depth. And so the template file that you started with and the calculations we went through were meant to one by one find the length of each individual segment until we got to the normal depth upstream, and then we added up all of the individual lengths to find the cumulative length. So it's a great procedure, but it has some limitations. When you're calculating the difference in energy between locations, excuse me, you have to assume that the cross section isn't changing between sections. And so at Y7 and Y6 the depth is changing, but the width of the channel can't change. And so this method, this direct step method, is just limited to situations where the channel shape is constant. And in applying that, you calculate the segment length, but it's not applicable to the broad range of conditions that you'd see in the real world. In the real world, streams are changing width, and streams may have adjustments that would make this direct step method not applicable. So we're going to talk about the standard step method, which is a step beyond. The direct step method only applies to a cross-sectional shape that isn't changing, and the standard step method, by contrast, can be used regardless. So we're going to go through the mathematical underpinnings of the standard step method before we look at the spreadsheet template that I shared with you and use it to solve an example, but I have to start with a warning. In everything we do in the standard step method, 1 and 2 is a little bit different than the way we've used those numbers in the past. In the past, whenever we had a 1 and a 2, we used it by saying that 1 was upstream and 2 was downstream. In other words, the water was always going from upstream 1 to downstream location 2. Here in the standard step method, 1 means the location where you know something, like the depth, and location 2 is the spot where you don't know the depth. So it doesn't necessarily mean upstream, downstream anymore. And you can see that in the figure that I've got. So in this figure, our location 2 is the upstream location, and location 1 is downstream. So in this example, what we know is the depth here at the downstream location, and we'd be trying to predict, we want to find out how deep is the water upstream. Now whether we work upstream or downstream, like what direction you're solving the unknown, traditionally depends on whether your conditions are subcritical or supercritical flow conditions. So what's shown in this figure is a subcritical flow, where we're going to start with the depth that we have measured, this known downstream depth, and we're going to try and predict what the depth would be upstream. Supercritical flow, you work in the opposite direction. So if you check the Froude number, or if you compare the critical depth to the normal depth, either one of those can diagnose the flow regime. But if you diagnose the flow regime and find conditions are supercritical, then location 1 is upstream, location 2 is downstream. All right. So with that warning, keep it in mind, we're going to apply a total energy balance. And so you can get the sense from the figure that what we're going to add up between location 1 and location 2 is the elevation above a datum, so that's Z. The Z term is how far above the datum it is to the channel. And then you add up the water depth, and those two things together, the Z and the water depth, we collectively are going to abbreviate that as WS, and that means the water surface elevation at a particular location. So WS1 is Z1 and Y1. WS2 is Z2 and Y2. So in the energy equation that's shown here, we're adding the water surface and then a little bit more to get us up to the total energy line, so the velocity head. And then here at location 1, we're also adding in the head loss between the 2 points. Now remember that if we have non-uniform flow, the slope of the energy grade line is not parallel to the channel slope. So we can't calculate the head loss just as simply as multiplying the distance L by the channel slope. That doesn't work, but we do have another method. Okay, so just as the starting point, this is the energy balance behind our method. We're comparing how much energy there is at 1 to how much energy there is at 2. Now here's the method that's encapsulated in the template file I sent you. First of all, here's the procedure. We're going to have knowns. We'll know the depth at 1, and we're trying to figure out what the depth at 2 is. And so we have to start with a guess. And we've done that a lot this semester. I think you'll remember many different procedures where we didn't exactly know, for example, what the amount of head at the junction of 3 pipes was when we did the 3 reservoirs method. So we started with a guess. Or when you applied the Hardy-Cross method, the loop method, you'd start with a guess. So we're doing that same thing here, where we're trying to predict how deep is the water at 2, but since we don't know, we'll start with a guess. So you'll start with a guess for the depth Y2, and you'll add that to Z2 and come up with an assumed depth for the water surface elevation at 2. And you can sometimes do better than just a random number. You know, if you look at the water surface profile classification and you find out that you have a mild slope and it's a type 1 profile, then maybe that would tell you that Y2 is a little bit deeper, or excuse me, a little bit shallower than Y1. And so you can get some clues and hints on what to use as a reasonable starting point by the water surface profile classification. Now, once you have a guess for what is the depth at 2 and the water surface at 2, so on the basis of that guess, you're going to determine the observed head loss with this formula. So the observed head loss will just be the difference in the total energy at 2 minus the total energy at 1, where the total energy that we're talking about is the water surface and the velocity head. That's the observed head loss. We're going to keep track of something we call the calculated head loss. And the calculated head loss uses Manning's equation to estimate the average slope of the energy grade line. And so remember, S sub F, the slope of the energy grade line, comes from Manning's equation. So this formula is, we just rearranged Manning's equation to solve for the slope. So we're saying, what's the slope of the energy grade line? And then the bar on the top here means the slope at the midpoint, midway between location 1 and location 2. So we're going to estimate how much energy loss there is with two components. There's the part of the energy loss that has to do with the flow through the channel, and then there's the part of the energy loss that has to do with any kind of a transition, like, you know, how we have friction losses and local losses. Well, here the analogous part of that is the S sub F times L would have to do with the friction loss, and then this has to do with the changing shape, because when we've studied this before, when we had transitions, when there's an expansion or a contraction, there may be an expansion or contraction coefficient C that describes how much energy is lost because of that transition. So we'll do the same thing here with the calculated head loss. We'll account for the things that contribute to the calculated head loss. So we'll compare the two, the observed and the calculated head loss, and use, if they're not equal, then that tells us our guess wasn't accurate. So we have to come up with a calculated water surface elevation. So it's kind of a way of updating and getting closer towards a convergence for this numerical method is in the formula here, all of these terms will be known except for water surface calculated at 2. So we'll calculate what the water surface should be. You know, this is kind of like an improved guess for it instead of just the one we started off with, which was, you know, a less accurate guess. This will be now, solving for this will be a more accurate guess, and then we come up in the next iteration with an updated value by averaging our previous value with this updated version. Rather than just using this updated version directly, we average the last one and this one, and it converges more efficiently that way. Okay, so that's the background. I mean, that's how this spreadsheet came to be. That's what we're trying to accomplish with the different columns that are in there. You know, the textbook didn't have this spreadsheet. I came up with a spreadsheet after going through this procedure and trying to figure out kind of what data would we need to solve problems like this. And then you do it as many times as you need until you have matching between the observed and the calculated head loss. So that's how you know when you don't need to repeat the process with any further iterations, is when the two things are equal. This is how we are going to apply that method. We're going to deal with the case where downstream we have a trapezoidal channel, and upstream the channel is rectangular. So think that what's happening is that the water upstream, so section 2 is upstream, and it's rectangular, and what's happening is that the sides are laying down as the water flows downstream, because by the time we get to section 1, the sides aren't vertical anymore. They're laying down at a 2-to-1 slope. The bottom width is staying the same, 25 feet. So what we want to know is how deep will the water be in section 2 if we have 1,000 feet of distance between these 2 points, and we know that the elevation of the bottom of the channel is 5 feet at section 1 and 7 feet at section 2. So we know the delta Z difference between the 2 sections. We know how far apart they are, the flow rate that's going through the channel, the Manning's roughness value, and then the C, the expansion coefficient, having to do with the transition between a rectangular and a trapezoidal channel. Alright, so that's the background. Now, the first thing that we need to do is calculate the normal depth and the critical depth, because we want to make sure that we have subcritical flow, because I mean it's kind of implied in this problem, because I already told you section 1 is downstream and section 2 is upstream, and so that's implying that we're working in the upstream direction, which is what you do for subcritical flow. But the way that we would determine that is by some hand calculations. So let's look at those together. The horizontal distance between the 2 locations is 1,000 feet, and the elevation difference is 2 feet, and that comes from the invert of 5 versus the invert of 7. Okay, so the channel slope is 0.002. The normal depth we get from Manning's equation, and here's the geometry of our trapezoidal section. At the trapezoidal section, then like at the location where we know things is here at section 1. So what we want to do is we want to compare the flow depth to the critical depth to the normal depth. Those 3 things tells us what kind of a profile we have. So at this location where we have the measured depth, what would be the normal depth there? Well, we have to use, for the area, 25 times the depth plus 2y squared. That's just the formula for the area of a trapezoidal channel, and we have the wetted perimeter formula for a trapezoidal channel. So I know that you could solve for the normal depth because I've had you do it before. I've had you solve in exams the normal depth for a trapezoidal channel. And so if you go through that process, you'd get that the normal depth of flow is 6.85 feet. So you can see here we made the substitution of the flow rate, and then the 1.49 is because we're working with traditional units. And we got the n value, and so all the parameters there, and we calculated normal depth. So next we have to calculate the critical depth. You've probably gotten into the habit of calculating critical depth by flow per unit width divided by, flow per unit width squared divided by g to the 1/3 power. And that's a great formula if the channel is rectangular, but this is not a rectangular channel. So we can't use that simplified formula that we've used in the last couple of class meetings for the normal depth. Instead, what we have to do to find the critical depth is solve the Froude equation. So the equation we have for Froude number is that the Froude number squared is the flow rate squared times the top width divided by G times A cubed. All right, so what is the top width of this channel? Okay, so if we have a depth of y, then what that means is that the top width on this side would be 2y, and there would also be a width over here that has a length of 2y. So that would make the total top width 25. So this length plus 2y over here and 2y over there. So that's 4y. So here's the equation. 25 plus 4y will be the top width. And then our area would be 25 times y plus 2y squared. We're going to take that to the third power. So solving for the critical depth is 3.35 feet. So if you compare normal and critical depth, anytime the normal depth is more than critical, then that tells us that we have a mild slope. And then our actual depth, the problem statement says that our measured flow depth here is 5 feet. So a given flow depth of 5 feet is between the normal and the critical depth. So that means that we're in zone 2. This is an M2 profile. Let's refresh our memory what an M2 profile looks like. Let's go back to that. Okay, here we are. An M2 profile, so it's mild when normal is more than critical, and then zone 2 is when the flow depth at that location is in between those two bounds. And so an M2 profile is getting deeper upstream. So remember, our location 1 in this example is downstream, and that's where it's 5 feet of depth. And we want to know, if we go upstream 1,000 feet, what's the new depth going to be. So where we measured, it's 5, and an M2 profile means it's getting deeper. So keep that in mind, because I'm going to start with a guess. So before we get into the spreadsheet, any questions on these preliminary calculations where we were calculating the normal or the critical depth? No? All right. Here's the template file that I sent to you. If you have that handy, please open it up. Okay. So you can see that I've pasted the little sketch that shows the channel characteristics downstream and upstream. So we're going to work at section 1 where we know the depth is 5, and the whole point of this exercise is to find out how deep will the water be 1,000 feet upstream if it's going from a trapezoidal to a rectangular channel. So what will be the new depth? All right, so let's put in some of the information that we know and start filling in this template. All right, the flow rate, let me zoom in a little bit. It's 1,000 cubic feet per second. And hopefully you're able to follow along. I'd be curious to know how many of you ended up getting a second screen. Even if you're just doing it on your phone, hopefully you can work on one screen while you observe on another. Okay, we got our 1,000 CFS for the flow rate. Manning's roughness for this channel is 0.05. That would be given information based on, a field visit just to see how rough the channel is. Now Z1 is what's the elevation of the bottom of the channel at location 1. Sounds like I got a question here. Split screen with a laptop. Hopefully you've got good eyes. Okay, Z1 is 5 feet. Z2 is 7 feet, and that comes from the sketch, the invert that it's talking about. That's the elevation of the bottom of the channel above some datum. The coefficient for expansion / contraction, I think in the problem statement it said that that is 0.3. So 0.3. And finally, we are going to put in our length of 1,000 feet. Okay. So just putting in the preliminaries there. Let's put in the information where we know some things. The known section, we know that the water depth is 5 feet. And now where it's known is the trapezoidal channel. And so, for example, the area is going to be 25 times the depth of 5 feet, and then the side area as well of the triangle will be 5 times 10. So we're just getting the area of the trapezoid here. So it is 25, because that's the channel width at the bottom, times the depth, plus the depth times 2 times the depth. I guess I could put in just like the strict numbers, but like if you're wondering where that comes from, we just want to know what's the cross-sectional area for section 1. So if you look at 5 times 25 gives you the rectangular part of it, and then we have these two triangles on either side with a height of 5 and a top width of 10. So I was being a little convoluted by putting the cell references in here. It's 25 times 5 plus 5 times 10. 175. All right. So what's the flow velocity? Well, V equals Q divided by area. So Q divided by the area tells us that the velocity is 5.7 feet per second there. The wetted perimeter, that's a little bit more involved than the area was. It's going to be the bottom distance of 25 feet and then 2 times the side. And so it's going to be 2 times the square root of 5 squared plus 10 squared. Oh, somehow I've made a mistake there. Oh, plus. This should be plus, not times. Plus. So that's the wetted perimeter. So it's the distance on the side of the trapezoid and the bottom distance. So let me show you that formula again just briefly. Okay. Now the hydraulic radius is the area divided by the wetted perimeter. That's the definition of hydraulic radius. And now E1 is going to be the depth of flow and the z value, and then also we have to add in the velocity head. All right. So let's just leave it as the depth of flow and the velocity head. Let's make it a specific energy that's above the channel bottom. Okay, so it's the depth of flow plus V squared divided by 2g. And remember, as a caution, we're working in traditional units here, and so g is 32.2. Okay, so let's see, I think I've made a mistake here. I forgot the z. Yeah. Okay, let's add in the z. Thank you. Okay, so the energy at 1 has all of that, and now the slope of the energy grade line, we're going to use Manning's equation for that. And so you can see Manning's equation is here. And so let's have, first of all, the parentheses, n with the anchor, the reference there, times q, and to anchor that reference, oops, divided by 1.49 times the area times the hydraulic radius to the power of 2/3, so 0.6667, and then all of that is going to be to the power of 2. So let me pause for a moment, make sure you've got the formula, and what we're looking for is that the slope of the energy grade line at section 1 should be 0.00644. Okay, I see a question for R1 and E1. Okay. R1, the hydraulic radius, is the area divided by the wetted perimeter. So we have A1 and P1, so you get R1 by dividing them. E1 is the depth, the velocity head, and Z1. So Z1, Y1, and the velocity head. And I guess while I'm looking at it, I should probably anchor the reference up there to the Z1, since that's up in the header. And then finally, the formula for the slope of the energy grade line, I've just typed in this formula, Manning's equation, so you can see that there. Okay. Any further questions before we continue? All right. Well, when we did the hand calculations, what we learned was it's an M2 profile. And in an M2 profile, it's getting deeper upstream. And so what we should say is it's going to be a little bit deeper than this initial guess we had for Y1. Okay, comment here from Maggie that you've typed out what you have. You have something different. Well, if it's the same formula and the same numbers, it should give you the same answer. We may need to look at it together after class if you continue to have a discrepancy, because I can't know what to suggest how to fix it without seeing it. Let's start with a guess of 5.1 as the depth at this upstream location, at location 2. And so if the water depth is 5.1, then the water surface will be the depth of water plus the Z2. So anchor that reference. Something tells me I clicked in the wrong spot. Oh, plus, not times. Plus. There we go. So we're adding them together. You know, from the side view, the water surface is depth and elevation above the datum. So water surface at 2 is Y2 and Z2. All right, it's rectangular, so the geometry is a little bit easier for the cross-sectional area. The cross-sectional area is just the 25-foot width multiplied by the depth. So we know it's 25 feet wide, and Y2 would be our area. So velocity is the flow rate, Q, divided by the area. So we get the velocity. Wetted perimeter for a rectangular channel like this, the wetted perimeter is 2 times the flow depth plus the bottom of the channel, the width of 25 feet. Okay, so our wetted perimeter should be 35.2 feet. And the definition of hydraulic radius is area divided by wetted perimeter. And then the E2 is going to be the velocity head and the depth combined with the elevation above the datum. So those two things combined are the water surface. And so for E2, I can just say water surface 2 plus the velocity head. So V squared divided by 2 times 32.2. And be careful with those parentheses because we want to divide by the entirety of 2 times 32.2. So you should get that the energy at location 2 is 13.055 feet. And now we're going to use Manning's equation again to solve for S sub F2. Okay, so that's going to be N times Q divided by 1.49 times the area times the hydraulic radius. I'll type that in because I can't click on the cell location since my formula is in the way. M30, and that's to the power of 2/3, 0.6667, and then close parentheses so that I can take everything to the power of 2. All right. So we get, for this location, the slope of the energy grade line is 0.01245. All right, next, the observable head loss. Now the observable head loss is E2 minus E1. So if I scroll up a bit, I think you'll see the formula here that tells me what observed head loss is. So observed head loss is E2 minus E1. And for the average slope of the energy grade line, that S sub F bar, we're just going to average the two that we've already calculated. So it is this energy, this one plus that one divided by 2. So it's the slope of the energy grade line in the midpoint. Now for calculated head loss, we'll use this formula. Okay, so it is the slope that we just calculated multiplied by the length. The length is 1,000 feet, so anchor the reference to the length, plus the C value. By the way, was there a question? That was a little fast. Well, we've got 8 minutes left to finish this example, so it's going to be a little fast. All right. Slope of the energy grade line times the length plus the C value. So here is the C value. Anchor that reference. And then we need to have the difference in the multiplied by the absolute value of the difference of the velocity head squared. So we've got to have the absolute value of v2 squared divided by 2g minus v1 squared divided by 2g. All right, so that's going to be here, v2 squared divided by 2 divided by g. So that's the velocity head at 2. Is there a question? Okay, and now the velocity head at 1. v1 squared divided by 2 divided by 32.2. All right. So our calculated head loss should be 9.578, and that's feet. Now, you know, some of these formulas get a little bit complicated, and so I recognize you may need to go back through this video later on to catch up if you diverged your solution from what's going here. But just so that we have the whole method illustrated, let me show you where things continue to go. So our calculated water surface we'll now get from this formula. Alright, so we're using this one to determine the calculated water surface. So it's water surface 1, which is the Z1 of 5 feet and the water depth of 5 feet. So that's 10 feet. So water surface 1 is 10 plus the velocity head at 1. So v1 squared divided by 2 divided by 32.2. So that gives us the velocity head at 1 plus the calculated head loss, which we just had here, minus the velocity head at 2. So minus v2 squared divided by 2 divided by 32.2. Okay, so that gives us a calculated water surface at 2, and now the updated will be the average of the previous one and what the water surface calculated is here. I think someone has their microphone on. I hear a crying child. Or a goat. Okay, so it is the calculated water surface, and then our previous guess of the water surface was this one, divided by 2. Okay, so you can see I've got a cell here for the difference if we want to find out how much things are changing on a percent basis. It would be the current updated value minus the previous one divided by the new updated value times 100. So we had a 22% change. with this iteration. Now things get a little bit easier. Once you put the formulas in the first row, then you can continue. So let me just show you how, we can drag all of these down from our initial known section, and it shouldn't change any of these, so it automatically was changing the depth, but we can adjust that. James. Alright, so now for this new depth Y2, we get that from this updated water surface here. And so this new Y2 is going to be based on the updated depth. So this will be the water surface at 2 minus the delta Z. We know the delta Z is 7 feet, so minus 7 feet. Okay, so now that gives us a new guess for what we should use for the depth. And now all of these I can drag down a row. And so now we get some new updated guess for what the water surface ought to be, and it changes a lot less than it did. Already we're converging. We had a 22% change in the first iteration, now only a 2.6% change in the next iteration. And so the next value for our guess depth looks at the previous water surface minus out the invert elevation of 7 feet. And so this whole thing can be dragged down another iteration, and in fact we can just go through the bottom of the page here and see whether things converge. So our guess, initially we guessed maybe the flow depth upstream is 5.1 feet, but then we said 8.62, that was a little too high, and so eventually it stabilized, and we now know that the depth upstream is going to be 8.05 feet. And you can see that the percent difference, that the change for each successive iteration isn't going any differently. Jeffrey asks, can you show the difference gain again? The difference. Yeah, how to do the difference formula. It is the let's see, it would be the updated water surface minus the initial guess for water surface divided by the updated times 100. Alright, well it's 1:49. We're out of time. So what I'm going to do is send you this finished spreadsheet. I think you'd be better off just going through the video a second time and figuring it out, but at least if you, hopefully you still will do that, but having this finished solution as a secondary reference so you can check your numbers, I hope that will be useful. But I'll email you this as soon as we sign off for today's class, and then my suggestion is, get this example up and running, because we're going to have another example for that recorded lecture in Friday's class. So just to revisit the announcements here, the lecture material for Friday will be a recorded video that I'll email you Friday night. The assignment is due. Our final exam will be a Friday after that. So this is our last live class meeting of the semester. I've really enjoyed it. I appreciate your attention and your hard work. I finished grading the projects, by the way, and I was really impressed. I think, by and large, people exceeded my expectations and even my hopes. So thank you for all of your good work this semester. Hope you have a great day, and stay tuned. I'll send you the email with this spreadsheet file in just a minute. Take care.